Okay, we are still on 13, I think. And we talked about stoichiometry involving gases. And as we talked about, remember, it's pretty much the same sort of steps as a regular stoichiometry problem. Really, the only difference is somewhere along the way, you're going to probably use the ideal gas law. So you're still going to really balance your equation. You're still going to convert to moles. You're still going to determine whether or not it's a limiting reagent type problem. And then you will do your mole to mole relationship. And then finally your moles to some other unit. As I mentioned before, very commonly here at the back end, a little ideal gas law solving for volume is very commonly used. Also, occasionally up here in the front end of the calculation, again, using our ideal gas law and solving for n is also a very common sort of place where you would use it. Sometimes you might even use it in both places along the way. But that's pretty much the main difference there. Any questions on that there? All right, then let us continue on here. As I clearly wrote over the entire slide there. So let me just erase that there. All right. So we're going to talk about Dalton's law of partial pressures. And it sounds quite difficult, but it's not too difficult of an idea here. So the idea is, for example, a lot of gases will come as basically a mixture of different gases in the same container. So for example, if we had just a container here that had just gas molecule A flying around in it, and if this was the only gas molecule in there, the total pressure, which would be like your barometer reading, would be equal to basically just the pressure of A, as that's the only gas molecule that's basically in that container. Now, if we had a container where we had gas molecule A, gas molecule B, and C, and they're all flying around in that container. When we look at the total pressure of this container here, that's the result really of the pressure of A plus the pressure of gas B plus the pressure of gas C in this case. And because they each contribute a little bit to the overall pressure of that mixture, these are what are known as partial pressures, because they partially contribute to the overall pressure of that gas mixture. Now, how do we calculate a partial pressure? Well, most commonly, the way that we calculate our partial pressure is frankly the ideal gas law. And we use the ideal gas law and we solve for pressure. And we just solve for pressure really individually for each of the gases that are present. So we would do actually in this case, for example, 3 separate partial pressure calculations, which are really just 3 separate ideal gas law calculations. Just like normal, everybody's got to be in the correct units, right? When you go into the ideal gas law along the way. Now, helpful in this type of situation, and it's one of those things that pretty much things that make something an ideal gas is that there's no real interaction between gas molecules. So even though you may have some different gas molecules in the same container, it's almost like each of those gas molecules are in that container by themselves. And that's what allows us really to do kind of like 3 separate calculations, because gas molecule A is not going to be affected by gas molecule B or C that's flying around, and vice versa. All of them, they're not going to be affected by the presence of other gas molecules in an ideal situation. So the other nice thing about it is because they're all pretty much in the same container, they will all have the same volume. So the volume will be the same for all the gases. And because that container is sitting in the same room on the same bench, they also will have the same temperature pretty much. Will be the same in all these calculations. R is obviously a constant, which means really when you go to do sort of partial pressure calculations for each of the individual gases, the only thing that's going to be probably different are the moles. That's pretty much the only difference between all 3 of those calculations. All the other numbers will be identically the same for each of them. Again, because they're in the same container, and that container is at the same temperature. One calculation, the pressure of A, partial pressure of B, and you'll get straightforward there. Any questions on that there? Pretty much what this just says. Well, so again, we're just going to calculate each of them like they're in there by themselves. And then again, to get the total pressure, just going to add them all together like we just talked about there. Now, there could be a situation, for example, where maybe you don't have enough information to go into the ideal gas law. And there's another way that you could kind of figure out partial pressure. If you know much one pressure, either you know the total pressure of the mixture or you know somebody's partial pressure, you would be able to kind of figure out the partial pressures of everybody else. And we probably won't come across this too much, but since the slide's up here, I guess we'll talk about it. We could calculate what is known as the mole fraction, and this is the mole fraction. And if you have enough information to get to the moles of each of the gases present, you could be able to figure out basically the mole fraction. The mole fraction is basically the moles you're interested in divided by the total moles in that mixture. It's kind of like a percentage without times it by 100, basically. So it's basically how you calculate. And that would give us this equation here, which is sometimes helpful. That is the partial pressure of a gas. That is the mole fraction of that gas. And that is the total pressure of the mixture of gas. So for example, let's just say we had a mixture of gas A, and let's just say we had 2 moles of A. And let's say we also had B in there, and we had 4 moles of B in this mixture flying around. And let's just say we knew the total pressure of this mixture was 1.25 atmospheres. So, and this is really the only piece of information sort of given to us is the total pressure. We're able to get to the moles of each of these things. And we want to know the partial pressures of each of these gases. So for example, we could start with A. And what we could do is figure out for gas A, the mole fraction, which would be 2 moles of A divided by the total moles, which would be 6 moles in this case. And if we do that, that will get us 2 divided by 6. Gets us about 0.333. Basically 33% of it is A. We can then put it into this equation where the partial pressure of A would equal our mole fraction times our total pressure of 1.25 atmospheres. And basically here we would get 0.42 atmospheres in this case is the partial pressure of A. We could also have done that with B. We could have done for gas B, get the mole fraction of B, which in this case would be 4 moles divided by 6 moles, which is our total. And basically we'll take 4 divided by 6, gets us 0.667 as our mole fraction. Putting that in there, partial pressure of B will equal 0.667 times our 1.25 atmospheres will get us 0.83 atmospheres. And if you add both of those together, that equals a total pressure of 1.25. So this is a nice one that if you happen to come across a situation, and to be truthfully honest with you, I don't think you'll come across that situation in this class, but in 1A, whatever they call that class to come next, you probably will come across it. You could kind of use the mole fraction and the pressure or a partial pressure to figure out everybody else's pressure. Any questions on that there? All right, so let's take a look at one here. What is the partial pressure of helium and neon if they are in a 2.5 liter container at 27 degrees Celsius Calculate the partial pressures of each and also the total pressure of the mixture. Helium is 4.003, and it was neon, I think, 2018. All right, looking for three answers: partial pressure of helium in this mixture, partial pressure of neon in this mixture, and the total pressure. Okay, let's take a look. So basically, we have a container here, and we've got some helium in there. We've got some neon flying around. We know that this container has a volume of 2.5 liters. We also know it has a temperature of 27 degrees Celsius. So we do want to calculate the partial pressures, which essentially means we're going to use, again, our ideal gas law here. And we're basically going to use it twice, one for each gas. Before we do that, though, obviously we will need the moles. So we'll have to take our grams to moles here. So we'll start with our 5 grams of helium using the molar mass from the periodic table, 4.003 grams per mole. And that's going to give us 5 divided by 4.003. We'll call it 1.25 moles here of helium. We need to also do that for neon, so might as well just go right next door. 5 grams of neon. Also using the periodic table there, 2018 grams per mole. Going to get us here 0.248, we'll call it. So if we think about our ideal gas law here, we do have the volume. We just got the moles. We always have R, and we do have the temperature. So we really do have everything we need to go into the ideal gas law. We just got to do a couple of things here. Obviously, like normal, we got to convert our temperature into Kelvin. So we'll add a 273.15 to that. And that'll give us a 300.15 Kelvin. And again, we always have R, as we talked about last time, not usually given to you in a problem, but that is a constant value that, again, you should always have. So at that point, we're good to go here. We'll start with helium. And helium would be nRT divided by V, putting in our moles of helium, 1.25. Our gas constant and our temperature there, all divided by our volume of 2.5 liters. Liters will cancel, Kelvin will cancel, moles will cancel. Going to leave us atmospheres, which is good because that's the pressure. So 1.25 times 0.08206 times 300.15 divided by 2.5. Going to give us a 12.3 atmospheres. That would be the partial pressure of helium in this case. Any questions on that calculation? We're going to do it for the other gas there, which is neon. Pretty much identical calculation. The only difference here is the moles is going to be different. So we'll just cue it up here the same way. So taking our moles of helium in this case, 0.248. Our gas constant. And again, because they are in the same container, they will have the same temperature. And they will also have the same volume. And once again, the same units cancel, leaving us with atmospheres here and 0.248 times 0.08206 times 300.15 divided by 2.5 gives us about a 2.44 atmospheres. And that would be our partial pressure of neon in this case. Any questions on that so far? At this point, the only thing left to do is to get the total pressure. And I get the total pressure by doing what? Yeah, just basically adding these together. So we're going to take the partial pressure of helium plus the partial pressure of neon. We're going to do a 12.3 plus a 2.44 atmospheres. Going to yield us a 14.7 atmospheres in this case as our total pressure. Any questions? Yeah. Are you asking why are they not like diatomic? Is that what you're asking? Like the HE? They're not diatomic because all they're noble gases. So all the noble gases actually comes as ones. They're monatomic. So only like hydrogen, nitrogen, oxygen, fluorine, and chlorine, those guys which are gases, they come as twos. Other questions? Okay. By the way, the one that's contributing pressure is which gas? It is helium. Any reason why helium's contributing more, you think? Has to do with this number. Helium is much lighter, which means it's going to have a greater velocity. It can actually be flying around a lot faster because it's much lighter. And because it's flying around a lot faster, it's going to cause more collisions and contribute more to the pressure than the slower moving, in this case, neon, which is heavier. It's going to move a lot slower. Any questions on that there? All right. So that is definitely a very common way to do partial pressure type problems. Just really, as you hopefully could see, it's just an ideal gas law problem, just for each one separately. There's also another situation that becomes a partial pressure situation, and frankly, pre-lab discussion, that is the setup that you should have a little bit later on today. When we get to lab, that's what it should look like. You will have this guy right here, a little potassium chlorate, and you'll heat it up in the presence of that catalyst, which is MnO2. And when you heat this up, you'll get a little KCl plus some O2 gas generated in the case. As you start to heat this carefully, by the way, back and forth motion, not like torch it when later today when you get there. You will generate this oxygen gas. Oxygen gas will come through the tube into this beaker here or this container that's full of water. Gas will bubble in, water will come out. So it'll displace basically the water that's in your tube or in your container, kind of similar to what happened in the tube the last week when we did the magnesium. You will again be ending with a space here that's empty, and it's really not empty. It is where we will have, in this case, the oxygen, but we will once again here, as we talked about last week, we will have the vapor pressure of water as well. And the water that's in there in the gas state is really just in there because of the way that we collected the gas. So again, just sort of a byproduct of how you collected the gas, because again, the reaction is going to heat up the water and you will get some water vapor kind of coming out into there. We're not really interested in this reaction, for example, about the water, just like last week, we weren't interested in the water. We were interested in just the hydrogen last week. In this case, we're interested in the oxygen this week. And that means that we have to do sort of a correction here. And what happens, though, is that the total pressure in this case will equal the pressure of the gas plus the vapor pressure of water. This vapor pressure of water, as we saw last week, is a value that you can look up in a table typically. So you can look it up in a table based off of the temperature. And a lot of times when we go to do a calculation involving the pressure in this type of situation, we really want just the pressure of the hydrogen or the oxygen in this case. So we would rearrange this, and the pressure of the oxygen would be our total pressure minus the vapor pressure of water. This is really in the lab, your barometer reading. And that obviously is the value that you would look up on the table. This will sometimes give you what sometimes in experiments they refer to as the pressure of the dry gas. And they call it the dry gas because you're subtracting off water's sort of contribution to it. And the nice thing about this one is, frankly, just a subtraction type of calculation to figure out the partial pressure. So how do you know it is this type of situation? There's usually some words and book problems that let you know that looking like you collected the gas over water? Are you collected it saturated with water vapor? Those are keywords that you pretty much need to subtract off the vapor pressure of water to get the actual pressure of the gas by itself. Any questions on that? And again, that's pretty much what we're going to do in the first experiment right there. So again, we will subtract off the vapor pressure of water to give us our partial pressure of the gas we're interested in. So for example, if we look at this one here together, a sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr. The vapor pressure of water at 30 degrees Celsius is 31.824. What is the partial pressure of oxygen gas? So once again, when we see this sort of wordage there, saturated with water vapor, that's how we know it's sort of being collected over water. And we will have that situation, as we just talked about, where the total pressure in this case would be the pressure of the oxygen gas plus the vapor pressure of water. Now, in this case, they did give us the total pressure, which is 753 torr. We are looking for the partial pressure of oxygen. And if it was not given to you, you would have to go to the table that's probably in that chapter. And again, look up the vapor pressure of water at 30 degrees. They did that for us, which was nice. So 31.824 torr here. These also need to be obviously in the same units for everything to work out right. So if they're not, you do need to do some type of conversion. At this point, the partial pressure of oxygen would be just a subtraction situation. Total pressure minus the vapor pressure of water. And that's going to give us here 753 minus 31.824. Going to get us here 721 torr. They did want the answer in atmospheres, right? So a reminder that 1 atmosphere equals 760 torr. So to do our conversion here, 721 divided by 760. And that will get us here 0.949, we'll call it. This would be the pressure of oxygen, the dry pressure of the oxygen gas in this situation. So the nice thing about this pressure situation is, frankly, just a subtraction in most cases. So you just got to subtract off from the total pressure the vapor pressure of water that you can find on the table, and that'll give you the pressure of just the gas you're interested in. Once again, we need to do this because the water here is really just a byproduct of how we collected the gas. So it's not really what we're interested in. Any questions on that type of partial pressure? Obviously, as well, if you had a total pressure of all the gases and you had some partial pressures given to you and a total pressure, also can be a subtraction problem. You just subtract it off from the total pressure and it'll give you the partial pressure, whichever one's missing, for example. Any questions on this here? So let's finish up talking about gases. A lot of these we did sort of touch upon. Gases, as we talked about, consist of tiny particles, atoms, or molecules. The distances are the particles are really small compared to the distances between them. So the volume of the actual individual gas molecule is not really important. Question? Yeah. You can't calculate the density of a gas. Yeah. So are you asking, is the density related to what we were just talking about, or are you just asking in general to calculate, just in general to calculate the density? Yeah, you can calculate it. We'll talk about it in just a second. How's that? Yeah. So the particles volume themselves is considered really not important compared to the volume here. That is something that makes something an ideal gas. And in an ideal gas situation, we don't really worry about the size of the actual volume molecule itself or the gas molecule itself. We worry more about the volume of the container it's in. And as I mentioned, that's why a lot of times what you'll see is the volume of the container given to you in a problem rather than the volume of the gas. Particles are in constant motion. They're colliding. It's those collisions that cause the pressure we associate with them. Number four here is really the other thing that makes something an ideal gas, and that is the idea that there's no attractive forces or repulsion type forces between gas molecules, even if they're in the same container. And that is why what we just did with our partial pressure calculation allowed us to do that in an ideal situation, because even though they're all in the same container, when there's no interaction between those different gases, we can kind of do an ideal in there by themselves. When you get to 1A, you'll talk about real gases or non-ideal gases, and that happens at really large pressures and really small volumes, which means you actually do have to take into account the volume of the gas itself and also the interactions between different gas molecules. It will give you a ideal gas law that looks really scary, which is known as the van der Waals equation. It's got a lot of other symbols and constants. Uh, the interactions between molecules and also the volume of the gas itself. Good news is we don't use that here, but we need it. And a more universal sort of gas law to use, rather than something like the van der Waals equation, which is specific for each gas. They have different values that you have to use, stuff like that. The average energy or kinetic energy of a molecule is proportional to the temperature in Kelvin. And that was the idea, as we talked about, that as we increase the temperature, we would expect, again, our gas molecules to start flying a lot faster. And obviously, as we lower the temperature, we would expect them to travel a lot slower. These are a couple of the relationships we talked about throughout this chapter. Temperature, the higher the temperature, as we just mentioned, typically that will allow them to move faster, and it will also obviously usually increase the collisions as they're flying around faster. Lower temperature, they would be moving slower, less collisions happening. Pressure and temperature, if we have a volume that will not move, as we do increase the temperature and they're flying around faster, as we talked about with Guy-Lussac's law, we would expect the pressure to start to increase, and vice versa. If they're moving around slower, we would expect the pressure to start to go down. The adjustment of that happens in a Charles law situation. Volume is not fixed, and remember that tau is able to keep a constant pressure, adjusting in the increases the ground in and keeping the number of collisions constant, and that's what keeps the pressure constant. And as you lower the temperature, the volume will come down in a Charles law situation, and that will allow the collisions again to stay relatively constant. Any questions on that there? Yeah. So the question I think was about density of gases, and when we talk about density of gases, typically gases densities are actually in units of grams per liter, is typically the units of density that we see for gases. And if you think about the density, for example, right, it is mass divided by volume in this particular case. And this again is where we get our grams per liter. You could actually, if you have the right information given to you, for example, in a gas law problem, you could actually use the ideal gas law to figure out the density of a gas. And if you take the ideal gas law, for example, and you solve for N divided by V, that would be P over RT. And N is moles and V is volume, which is liters. That actually is, as we'll talk maybe a little bit today, that is what's known as the molarity of a gas. And P would be the pressure, would be all you would need. And T would be the temperature, and that's obviously the gas constant. And if you did all this, you would end up with units of moles per liter, but usually densities into units of grams per liter. So the liters part's good. The only part that's not good is the moles part, right? And we could go from moles to grams by using the molar mass from the periodic table. So if you know the molar mass of your gas, you can basically multiply it by the molar mass. The moles will cancel, and you'll end up with the density of your gas in grams per liter. So you got to use the ideal gas law, solve for N over V, and then times it by the molar mass of your gas, and you can figure out the density of your gas in a two-step process, I suppose. Yeah. Is that your question? Yeah. Okay. Other questions on that? All right. We're probably not going to do too much density of gases. You will in 1A, definitely. And also figure out the molar mass as well, for example, of a gas. I thought the ideal gas law. And that will give you the moles, and molar mass is grams per mole. That would be the moles, and usually in the problem, they will give you the grams, and you can divide the two and get the molar mass as well. So kind of very useful, the ideal gas law in a lot of situations that you can use it for. Any questions on any of that there?